All right, good evening or good day. I did take a week off recording just to give myself I guess, sanity. And then, of course, when I looked at the camera, I realized I was wearing a green shirt behind a green screen, and then I'm going to be a floating head, and I was too lazy to change. It's 2:30 in the morning, so I'm tired. I'm not changing. But anyway, hopefully everybody's having a good second week back from spring break. I do apologize. I didn't mean to put all the parts into your worksheet and have some of you guys freak out. I hopefully did say part one, part two. I do like you to explore part three after today. So I do apologize. But just remember, we're here for completion. Everybody's going to do well as long as you do it. And even if you turn it in late, I'm okay with it. We're in weird times. Last week was kind of depressing for me because I kind of knew that our school year is going to end. I kind of guessed that we're going to do it online. It wasn't like a hope, but it was kind of something that I knew that was a possibility. But now the fear last week set in that, what happens if we don't even start at the end of August? And how crappy that would be if we continue doing this in August. So I hope we don't. I hope we finally get to go back to class. I really do miss you guys. I miss seeing you guys. Staring at a computer just is not the same. Even though I'm loving my time with my son, I'm starting to run out of things to do. So I would like him to meet his friends as well and have fun instead of just being stuck with me at home all day. Anyway, I do want to talk about the basics of circuits. Like I said in the intro, we want to make sure that you understand kind of what it is. So one of the things that I asked you to do was, okay, well, let's say you had to put together a circuit. And a lot of times in the classroom, I'll give you a light bulb, two pieces of foil, and a battery, and ask you to light it up. Most people don't know anything about light bulbs. Like I said in the description, it's just things aren't incandescent light bulbs. But if you notice here, there's two wirings. In class, you wouldn't be able to see that. So a lot of people would kind of put both wires on the either end. You'll notice that the battery's on fire. Or they would put both of them at the ends right here, so at the tip, and you get the same result. So I always tell people when they're doing this, if the foil gets really, really hot or the battery gets really, really hot, you're doing something wrong, please stop. And pretty much eventually, either one person just knows from the beginning or eventually somebody luckily gets it. You touch one end and then you touch the side. So an incandescent bulb works where you have a dark metal thing, and most of you guys don't even notice it, but it's kind of a piece of paint that's there. So as the electrons are going into this direction, it goes through the filament here and comes back out this way. So that way it kind of completes something called a circuit. And that's kind of what circuits are. It's just a completion of a circular path. So when you look here, that's kind of what a definition is. I just Googled circuit. It's a roughly circular line, route, or movement that starts and ends at the same place. And for us, when we're talking about electrical circuits, we're talking about like pretty much between the terminals, the positive and the negative. So electrons are coming from the negative and they want to get to the positive end, even though in my next slide I'll show conventional current is positive to negative, but same thing. Electrons want to move from one end to the other, and it's going to do that. You can have something called a short circuit, and that's kind of what we showed in the very beginning, is if you connect them, and then we'll talk about resistance, something happens, and you'll notice that electrons are moving really, really fast if you short it out, and that's why it's dangerous. But when it's not shorted out, they're moving at a moderate speed, and that's kind of what we want. All right, so that's what a circuit is, just a circular path. So when we're talking about creating a circuit, we're creating a point from positive to negative ends. So for batteries, it's the one end to the other end. For your outlets, it's the two prongs that you're going back and forth. So that's the goal of electricity, to get from one end to another. One of the big things is something called voltage. And when I made you guys watch the story of electricity, Voltaic was able to pretty much get this named after him. And it's pretty much the amount of energy an electron has. So you could kind of think of it as, I guess in the case of water, it's kind of the how much it falls or how much energy it has to do work. So in terms of water, and you think about river, because a lot of times people will incorporate like electricity with water because it kind of makes sense. The flow of electricity, the flow of water. So if we're going to do an analogy of electricity with water, think of it as voltage is how high the waterfall is or how high the dam is. So if the waterfall is really high, the water is going to have a lot of energy falling down, potential energy, MGH. So if it's really high, it has a lot of energy to do work. So as it falls all the way down, it's more capable of doing stuff. Voltage is the same thing. If it has a higher voltage, the electron has more energy to do things. So when you're talking about something that's like 5 volts or even your batteries, all your batteries are 1.5 volts, it doesn't have that much energy. So if you put your fingers on both ends of a battery, do I have one near me? No, I don't. It's not going to shock you because 1.5 volts isn't enough. A 12 volt battery isn't enough. So you can touch both ends of the positive and negative and nothing will happen. I don't know the exact time where it actually does have enough energy to go through your body. I never experimented myself, but I do know 120 is plenty. So I accidentally touched both ends of an outlet before when I used to make computers. And it's a very uncomfortable feeling having electricity go through you. So voltage is how much energy it has. We're conductive, but it takes a lot of voltage to go through us, or energy of electrons to kind of force it through us. I like this picture because it kind of goes through the different energy pathways. And I think in our other one, when we talk about transformers, these are kind of where the transformers are. So the power plant makes about 30,000 volts. And then you have something called a step-up transformer that bumps it up to 500,000 volts, and then it could travel through. And then you have step down transformers to kind of lower it as it gets closer and closer to your house. So at the end, it's about 120 for us. I believe in most European countries is 240, but those are safe. Like it'll go through you, but it won't kill you. But 500 volts, 1,000 volts, it's going to kill you pretty much instantaneously. So that's why we have lower voltage around our homes. But remember, voltage is the amount of energy that electron has. That single electron, it could be a group of electrons, but that electron has. You could also think of it as just like a ball. So if you drop it from higher up, it's going to have more energy to dissipate if it hits you. All right, the next term I want to kind of talk about is current. So current is the flow of electrons. I guess the more accurate is 1 amp equals 1 coulomb. So just pretty much just know like flow. The higher the amperage means the faster the flow. And to kind of give you kind of reference in real world, and it'll make more sense once we talk about power and wattage, because we don't really rate our stuff. Like we don't rate our phone charger, or washer machine, microwave by amps. We actually rate it by watts. They're related. But for now, just to kind of give you an example, your phone charger depends what kind of charger it is, if it's those fast chargers or low chargers. But when it first came out, it was about half an amp. Now, then it went up to 1 amp. Now those super fast charger ones that could charge your phone in an hour, those are probably 2 amps. Your washer machine is probably the thing that's or the dryer is thing that's gonna take up the most energy in your house. So that kind of draws in about 10 amps. So like a heater, about 10 amps, hair dryer, 10 amps, microwave is actually not that much, 5. Your fridge isn't even that much. It's also about 5. And like your TVs now are ridiculously low. I think they're like half an amp. So it's really cool now that the things that normally used to suck up a lot isn't. Like the refrigerator used to be the one that sucks up everything. So now pretty much heating elements are the things that are going to suck up most amps or wattage, which we're eventually going to talk about. What I liked about this GIF is that you have negative here, positive here. Electrons do go from negative to positive, but Franklin thought the opposite. So when we're talking about current, we're always talking about positive to negative. If you mess it up, it's not a big deal, but we do know electron flow is to the right. Resistance is the amount of, I guess the best way to say is like how easily it is to flow through. So a wire doesn't have much resistance at all. So if I cut these two places, so copper wire, the resistance it's not 0, but it's practically 0. So when you do this, you do something called a short circuit. What I mean by short circuit is that there's no work that the electron has to do. It's super easy to get from one end to the other because there's no resistance, there's no work. If they want to, they can. So guess what's going to happen? All electrons want to move from one end to the other. Since nothing's slowing down, they go really, really fast. In the case for batteries, they go as fast as they can, so it heats up the reaction, so that's why the battery gets really hot. In your wire itself, if there's a lot of flow through it, there's a lot of friction through the wire, so what's going to happen is the wire is going to heat up, so that's why it gets hot. It's very dangerous in homes because if the wire heats up, it can melt or it could cause a fire, because usually our homes are made of wood. So as that wire heats up, it might catch things on wire. So we'll eventually talk about things called circuit breakers. But for now, just know that a short circuit is bad. So right now, short circuit, bad, because it doesn't slow down the electrons. So here is my light bulb. You'll notice that the electrons are moving, but not that fast. Now I can lower the resistance, and if it's 0, it gives me the same thing. 0.5, it's still going really fast, probably blow up my battery. And then we'll talk about how you'll notice that as the resistance gets bigger, my light bulb gets dimmer. But when it was very little, it was really bright. And we'll eventually get to that once we get to our power equation. But for now, we're just happy that. I could not believe, you can actually watch this on Amazon, but there was a movie called Short Circuit. So resistance is the resistance of flow. I forgot to type it in. I'll do it now. I apologize. Is measured in something called ohms. That's omega. So that's ohms. So that's kind of the measurement behind that. And this really doesn't make sense without the equation. The previous two, let me get rid of this. The previous two are amp is the amount of flow, coulomb is the definition, voltage is the amount of energy it has. But what really is the Ohm's law, how you define ohms is this. So you have V equals IR. This is the equation that's going to define everything. This is true for all circuits, kind of like when we did waves. V velocity is equal to frequency times wavelength. In this case, everything, when we talk about electricity, voltage is equal to current times resistance. I guess the best way to say is voltage over current will give you resistance. And you could kind of mess it around, but that's kind of how you define resistance. Remember, it's measured in ohms. What I'd like you to do, let me make sure, what I'd like you to do for tonight's homework is kind of explore part 3. So if you already did it, I apologize. I didn't mean to make you do it, but I guess you don't have homework for tonight. If you didn't do it, then do part 3 and then just resubmit it, or just submit it again. And then all that is just all the different types of circuits that you can have. So right now we're just talking about simple ones. Today I just kind of described it, but I'd like you to explore different types of circuits. There's series, there's parallel, and then kind of what happens to voltage, current, resistance as you change it. And that's kind of the next part of it. So hopefully you're going to have a good week. Hopefully I have a good week, I guess. And take care of yourself, stay safe. Hopefully we're at the end of this and we can slowly get back to normal. But yeah, still stay safe, still wear your mask when you go out. If you go out, try to do something fun. All right, take care.